Okay, welcome to another network optimization video. This one is talking about PERT slash CPM. I think these two acronyms have sort of been glued together. PERT stands for Program Evaluation and Review Technique, and CPM stands for Critical Path Method. And these are some techniques that are used to evaluate a project that has several steps along the way. And some of those steps have other steps as prerequisites. And so you can kind of represent the steps in the project as nodes. And so here we got step A, and it must be done before we can start on steps B or C. But we can do B and C in parallel with each other. And then D, we can start as soon as both B and C are done. Same with E. And then finally, F, we can only start once both D and E are done. Okay, and so here we're using nodes to represent activities, steps in your project or program. And the arcs or the links are directed arcs that represent the kind of precedence, and that A must be completed before B can be started. Okay. This is one way of representing them. I'll note that this is the way the book does it, of putting activities on nodes, and it's maybe the more common way to see it in practice, but it is now a little bit different from all the other network optimization problems we've dealt with, where our activities or our decisions were on the edges. So some things will be quite a bit different for this example compared with the previous ones. Okay. So our activities are on the nodes, and each activity has a normal time and a normal cost. Okay. And then potentially we can crash that activity, is sort of the technical term, which means that we throw extra money at that step in the problem, maybe by hiring extra labor, or paying somebody else to do it, or many ways we could throw money at the problem in order to reduce the time that it takes to do it. So each activity has a normal time and a normal cost, but also a crash time, which would be less than the normal time, and a crash cost, which should be higher than the normal cost. And so you can pay more to finish the activity sooner. Okay. So a couple questions that we might have when we have a project is, one, what's the soonest I can get it done if I don't crash anything? Okay. And so that's where the critical path and critical path method comes through, in that essentially we want to find the critical path, which is the longest path through the network. So this is kind of the opposite of the shortest path algorithm that we talked about earlier, where we wanted to find the shortest path through the network. This is really, we're trying to find the longest path through the network, because that longest path will really determine how soon we can be done, because every activity needs to be done. And we can't start the next activity until the previous activity, represented on the other end of an arc, is finished. Okay, and so looking at things, let's actually maybe do this one kind of for the normal time by hand. And so I'll create variables for when an activity can start. And so activity A is at the start. And so I'll say YA, which is when I can start activity A, equals 0. Activity A under normal time is finished at time 2. And so once it's time 2, then I can start activity B. And so YB equals 2. And I can also start activity C. So YC equals 2. Then activity B finishes at time, well, it takes 5 units of time. It started at time 2. And so it finishes at time 7. And so maybe I'll just maybe write as a note here, finish equals 7. And then for activity C, it finishes after 7 plus 2. So I'll just kind of write here, finish equals 9. Okay, so now activity D, its predecessors are B and C. B gets done at 7, but C doesn't get done until 9, and it can't start until both of its prerequisites are done. And so our start time for D, YD, is going to be the larger of these two. Okay. And E actually has the same prerequisites. And so YE is also going to be equal to 9. And then let's see, we'll finish. E will take 8 units of time plus the 9, and so that will be done at 17. D takes 6 units of time plus the 9, and so it will finish at time 15. And so if this finishes at 15 and 17 and they're both prerequisites for F, then YF, we can start activity F at time 17. And then it will take 3 units of time. And so we'll say then finish equals 20. Okay. So if we don't crash any of the activities, if we just allow them to take their normal time, we can finish the project in 20 units of time. So whether those are days, weeks, months, or hours, kind of depends on the context of the problem. I left the units off just to make this easy. But overall, we can finish this in 20 units of time. And so what's the critical path? Well, the critical path is the path that there's sort of no slack or waiting around along that path. And so if I look at this, this one finished up at 7, and then we weren't able to start this until 9. And so, and same over here, it finished at 7, but we weren't able to start it on 9 until 9. And so activity B finishes up before we really need it to, right? It's kind of got some what we maybe call as slack in when it can be done, and that it can be done as soon as 7, but it doesn't need to be done until it's kind of descendant activities, or the activities that come after it, don't start until 9. And so we'd say B is not on the critical path. On the other hand, C, it finishes at 9, and both of the activities that depend on it start at 9. And so C is on the critical path. Similarly, looking at F, F starts at 17, E finishes at 17, but D finishes at 15. So D is not on the critical path, but E is on the critical path because we finish it just in time to start its next activity that depends on it. Okay, and so sort of highlighting our critical path, in this case, the critical path goes from A to C, from C to E, and from E to F. Okay, and why is the critical path important? Because if we want to spend money to reduce the total time of the project from 20 down to something lower than 20, we only want to spend money on activities that are along the critical path. We have no incentive to speed up B because B gets done before we even need it to be done. Similarly, we're not going to spend any money to speed up D because it gets done before we even need it to be done. Okay, but we'd spend money on activities that are along that critical path because reducing their time will actually have an impact and reduce the finish time. Okay, so the critical path is the path where the finish of the activity is equal to the start of the next activity along the path, is maybe one way to think about it. I find it maybe easier to pick out which activities are not on the critical path, ones where they finish before the thing that depends on them has to start. Okay, so now let's maybe thinking ahead into crashing activities. We can spend money to reduce the cost of some of these activities. We're going to formulate that as a linear program. Okay, so let's formulate it as a linear program. To formulate it as a linear program, we want to say, what do we want our finish time to be? And so maybe we've got a deadline and the deadline is sooner than 20. And so that's going to be essentially one of our constraints, and our goal is to minimize the total cost of the project. Okay, which will include the normal costs as well as any crashing costs that we incur. Okay, and so let's talk a little bit about crashing. So let's see. Let's maybe draw a little graph here with time and money. And so for a given activity, there's going to be the normal time, which is going to be larger than the crash time. And so maybe we'll put a point there. That's the normal time in normal money. And the crash time is going to cost more money. Okay. And so essentially this is kind of our choices is we can, we sort of make the assumption that we can partially crash an activity and that we don't have to go all the way and crash it its full amount, but we can't crash it more than the kind of crash time, okay, or incur more than the crash cost. And so the idea is that we can choose essentially any point on this time between normal cost and normal time and crash cost and crash time. We're able to lower the time as we move up this line over here, but at increasing cost. And the way we sort of do this, or how we do our decision variable, is we have a variable for that activity. And so maybe we'll say this is for activity A. And we'll call that XA, which measures the amount of time that we've crashed. Okay. And so some constraints that we get here is that XA, the amount that we crash, can't be less than 0. So we get non-negativity for it. And it can't be less than the max, the total amount that we can crash. And so that would be time normal minus time crash. So that would be the total amount of time that we could crash is sort of the difference between those. And then our cost of that activity, if we kind of think about it, is we want to look at sort of the slope of this line and use that and kind of figure out what's the marginal cost per unit that I'm crashing. And maybe the little bit tricky thing is that our amount of crash variable is sort of pointed this way. But we can essentially compute the slope of this line, which would be the change in cost. So I'll use C for, yeah, I'll spell out cost crash minus cost normal over time normal minus time crash. And then we're going to multiply that by the amount that we crash. This is essentially the marginal cost of crashing, which is the cost per unit that we crash. Okay, so this is sort of our marginal cost per hour or week that we reduce off the time of that activity. Okay, so then if this is going to be the cost, maybe let's rewrite this as, I'll just call it marginal A. Then our objective is going to be to minimize the sum over all nodes, because the nodes are where our activities are, of the marginal cost for that node multiplied by the amount that we crash for that node. plus the normal cost for that node. No, I should put some N for normal cost there. Okay, so it's going to be our normal cost plus our crashing cost. So maybe I should make that a little bit clearer here. That's our crash, maybe crashing cost. The kind of cost for the crashing. So normal plus that cost for crashing. And we want to minimize this. But what are our constraints going to be? Our constraints are essentially that we can't start an activity before we finish its predecessors. Okay, and precedence is denoted by these edges. Okay, and so we're going to get a constraint for each edge, and maybe I'll note the edges as I'll write it as ij. So this would be connecting node I to node j. Of course, I don't actually have I and j here, but I is going to represent one of these start nodes, and j will represent the end node for that activity. And so for each edge ij, we're going to, I is going to be the predecessor activity. And so the start time for the predecessor activity plus the time that it takes to finish that activity. So that would be time normal for that activity minus the amount of time that we crash off that activity. So that would be xi. And so here's when we start. Here's how much time it normally takes. If we subtract off the crashing time, this gives us the time that it actually takes. So start plus time it actually takes gives us essentially when it finishes. And so this is when activity I finishes, and it has to finish before we can start activity J. Okay, so for each of our edges in here, which represents a precedence relationship, we need to finish the previous activity before we start the next activity. And yeah, so we get a couple sets of variables. Our X's are the amount of time that we're crashing, and our Y's are the start time for each activity. Okay, so this has been an overview video of it. In the next video, we'll jump into how do we implement the linear program in R.